Welcome to Spring LIB.
All right, we need to determine whether for each of the species that we'll look at whether they are cyclic conjugated systems, then determine the number of electrons in that cyclic conjugated systems, entering 0 if it is not cyclic or conjugated, and then determine whether it's aromatic, anti-aromatic, or non-aromatic. Our first system is the following. Okay, do we have a cyclic system? Yes, we do. This is cyclic. Do we have a conjugated system? Again, yes, we do. How do we know? Because all of the carbons in this molecule, or at least in the cyclic portion of this molecule, which to be honest is all we have, are sp2 hybridized. And then recall that if we have nitrogens or oxygens, that they will adjust their hybridization when in a system with nothing but sp2 hybridized carbons to also be sp2, meaning that this oxygen will hybridize as sp2, and one of its lone pairs will be in an unhybridized p orbital, sticking up out of the plane, the same as the p orbitals creating the double bond between the sp2 carbons. Therefore, we can determine that this oxygen will contribute 2 electrons because of the 2 electrons that are in that p orbital, which is in fact what is defining our conjugated system. Oxygen contributes 2 electrons. Carbons, which participate in double bonds, always contribute 1 electron to the conjugated system. Therefore, this carbon contributes 1 electron, and this carbon contributes 1 electron for a grand total of 4 electrons, which is the answer to question A, how many electrons are in our cyclic conjugated system. As for part B, recall that from the 4n plus 2 rule for aromatic systems must contain, starting from 2 and counting upwards by 4, 2, 6, 10, 14, 18, etc. electrons, and that anti-aromatic systems contain, starting from 4 and counting by 4s, 4, 8, 12, 16, 20, and so forth electrons. In our case, we will look to the number of electrons we have in our cyclic conjugated system, which is 4, and determine is that on the aromatic list or the anti-aromatic list. It's on the anti-aromatic list, which tells us that our cyclic conjugated system is anti-aromatic. If we had an odd number of electrons, which wouldn't be on either list, our system would be non-aromatic. That is the first molecule down. Let's look at our second compound. Okay, first order of business, do we have a cyclic system? Indeed we do. We can see our cyclic system right there. Note that we will not be considering the molecule which lies outside of our cyclic system, the atom which lies outside of our cyclic system. Next, are the species present in our cyclic system sp2 hybridized? Indeed, each of the carbons which participates in our system is also participating in a double bond, which tells us that these are sp2 hybridized. Are our nitrogens sp2 hybridized? Yes, right? In the same way that carbons are sp2 hybridized when they participate in double bonds, so too are nitrogens. Recall, in fact, as well, though, that just like oxygens in our previous examples, if they're surrounded by sp2 hybridized carbons, they will adopt their hybridization to also be sp2 hybridized. There is something important to note about these lone pairs, however. When we consider the hybridization of these nitrogens, note that they are hybridized such that their sp2 orbitals, of which there are 3, lie in the plane, like so. There's one sp2 hybrid orbital. There's the second sp2 hybrid orbital. And the third sp2 hybrid orbital in the plane is what contains the lone pair. The unhybridized p orbital that's participating in the conjugated system does not contain the lone pair, as does the oxygen in this example, or nitrogen in other examples when nitrogen is not participating in a double bond. So in this case, this nitrogen contributes exactly 1 electron because the electron it's contributing is 1/2 of this double bond that is participating in. All right, so whenever you have a nitrogen with a double bond and a single bond and a lone pair, the lone pair is outside of the ring. It is not part of the conjugated system. In fact, it is the unhybridized p orbital which is contributing to our system, meaning this nitrogen contributes exactly 1 electron. Likewise, this nitrogen also participating in a double bond with a lone pair outside of the ring is contributing exactly 1 electron. And as we discussed before, carbons that participate in double bonds contribute exactly 1 electron to the conjugated system as well. Thus, we can see we have 4 carbons, each contributing 1 electron, as well as 2 nitrogens, each contributing 1 electron, for a grand total of 6 electrons in our cyclic conjugated system. If we refer back to the list corresponding to aromatic systems, we find that 6 is indeed on the aromatic list, which means that our system is indeed aromatic.